All right, now let's focus on titrations for a little bit. So titrations are going to be useful for finding the concentration of some known acid or base. And so let's just say here in this setup, right here, that we have a solution of HCl. And that HCl solution is in some container with a known volume. So we know the identity, we know the volume, but we don't know its concentration. So concentration is the goal. So how am I actually going to find the concentration? Well, I know that when I take a strong acid and I introduce it to a strong base, every single mole of strong acid can react with every single mole of strong base and cancel out. And that cancellation happens at a pH of 7. So this graph is specifically a strong base, strong acid titration curve. And for your exam, I wouldn't worry too much about looking at, weak acid and strong base, or strong base, weak acid, all the different combinations, because it's not going to matter too much about the technicalities of those graphs and what they look like. All you really need to know for titrations are some basic definitions and the basic process. So what's going to happen? Well, at a pH of 7, what actually is occurring? At a pH of 7, that is the neutralization point, remember? So all of my NaOH and all of my HCl are canceling out to form H2O and NaCl. So at the neutralization point, I have only H2O, and only H2O is going to have a pH of 7. So when I have this cancellation of NaOH and HCl, that point on the graph is going to be the equivalence point. And so how am I going to do this? How am I actually going to add the NaOH to the HCl, and how is that going to determine the concentration? Well, I'm going to have something called a titrant, and that titrant is going to be some liquid that I know the concentration of. In this case, our concentration, we haven't been told yet, I'll tell you that in a second, but we know it's NaOH, and when we drop it into this beaker here, beaker, graduated cylinder, I don't know. When I drop it into that vessel here, it is going to decrease on the measurement, and I'm going to be able to tell how much I've added. So if I know the identity, and it would be NaOH, and I know the volume, and I know the concentration, I can then use this as just a neutralization problem, where the concentration of the first times the volume of the first is equal to the concentration of the second times the volume of the second. So let's just say, for this example, we know that HCl, the solution, has a volume of 500 milliliters. So let's say that that HCl solution has a volume of 500 milliliters. So let's set this up as the M1V1 equals M2V2. And let's say that M1V1 is the acid, so concentration of acid, which is unknown. And the volume is 500 milliliters. And then we know our concentration of NaOH. Let's say that the concentration of NaOH is, let's just say 0.8 moles per liter. And as we add that NaOH to our analyte, we add our titrant to our analyte, and our analyte is HCl. As we add it, we are going to start to see a change in the pH. So we would start in our solution, if we've got like a pH reader, and we're measuring the pH of this solution, I could start off potentially at a pH of 2. And as I continue to add NaOH, I'm going to see the pH start to gradually shift. And it's going to start to shift closer towards the pH of NaOH as I add more and more of it. But what actually happens at some point, I don't just gradually change anymore. There is some definite range where I suddenly have this massive shift up in pH, and I will start to gradually climb off again and have little changes in pH. But so what you might need to know is that this graph for a strong base, strong acid titration curve follows a sigmoidal relationship, or it's a sigmoidal curve. And that just describes this shape that we have here. That is sigmoidal. So, as we get back to our original problem now, the concentration of the acid is unknown, but we know we have 500 milliliters of it. Our NaOH has a concentration of 0.8 moles per liter, and let's say it took us 80 milliliters to actually get to the equivalence point, to neutralize our solutions. Well, we know that the number of moles are going to be equivalent for a monoprotic strong base, strong acid at the neutralization point. So all I have to find is the equivalent point for HCl, or in other words, whatever is on this side of the equation must also be on this side of the equation. So my unknown molarity of the acid times 500 milliliters is equal to a value of 64. So 500 divided by 64 means that my pH of this HCl was 7.81, or that's my concentration of the acid, 7.81 moles per liter. That is a pretty high concentration. And do you know why? Because that's wrong. How did I get that? 64. Sorry guys, that is 0.128 moles per liter. And that would be the concentration of the acid, 0.128 moles per liter. So that's the only major relationship you need to know. Know what a titrant is, what you are adding, to the unknown concentration liquid, and then the analyte is just the solution of unknown volume or unknown concentration. Great. So Which of the following points best represents the equivalence point for a strong acid, strong base titration curve? It's going to be the vertical line. I'm really just messing up every other word right now. The point of a drastic change vertically will be my equivalence point. So that is best represented by position C. How much more acidic is a solution with a pH of 4 compared to a solution where the pH is 7? So for this, pH of 4, pH of 7, what is our actual concentration of H plus ions? For a pH of 4, that would be a concentration of 10 to the negative 4 moles per liter, so 0.0001 moles per liter, while a pH of 7 is 0.000001 moles per liter. So if I just compare these two numbers, I can see that a pH of 4 is 1,000 times more acidic than a solution with a pH of 7. So 1,000-fold. What is the pH of a 0.5 molar solution of CH3COOH, given that the Ka is 1.8 times 10 to the negative 5? Fascinating. So, what am I going to be after? Well, I need to find the H plus concentration. And if I know the Ka, which is 1.8 times 10 to the negative 5, then 1.8 times 10 to the negative 5 is equal to my dissociated CH3COOH, which will be H plus, and then CH3COO minus. And that will be over the concentration of CH3COOH, which is 0.5 molar. And we do have to take into account the fact that this is made up from the original amount of CH3COOH, but because it's a weak acid, we assume that's so little associated that we don't actually have to subtract any appreciable amount from that CH3COOH solution. So instead of finding some kind of unknown value for the amount that did dissociate, we just kind of say it's negligible. So the starting solution is still the amount that we have after the dissociation took place. So 1.8 times 10 to the power of negative 5 times 0.5 is equal to 9 times 10 to the power of negative 6 is equal to x squared. And now x is equal to 3 times 10 to the negative 3. And if that is our x, and I know that one of those x's is H plus, or that all x's are equivalent, that means that this is my H plus concentration. 3 times 10 to the negative 3 moles per liter. Let me just write that in. Why did I put brackets? Is equal to my H plus concentration. Now this is asking for pH, so I just have to do the negative log of 3 times 10 to the negative 3. And that will be 2.523. And that will be the pH. What is the pOH of a solution that has an OH concentration of 1 times 10 to the negative 6? Well, we're asked for the POH, we're given the OH, so this will just be a direct negative log of the concentration. And so, because we're just given 1 times 10 to the negative 6, you can easily just do this in your head. The answer will be 6. What is the POH of a 0.08 molar solution that has a Ka value of 1 times 10 to the power of negative 3? All right. So, long process again. 1 times 10 to the negative 3 is equal to the dissociated acid and base. We're given the Ka, so we're talking about the acid here. Let's just say that's A minus over HA, and HA is 0.08. So, 1 times 10 to the negative 3 times 0.08. That squared will equal 0.0089. So that is equal to the H plus concentration. So now, what am I going to do? Well, I'm looking for the POH. So what can I do? There's a number of different ways, of course, but I'm just going to take this number, do the negative log, so pH is equal to negative log of 0.0089. That is 2.051. And now at 2.051, that's my pH, and I know that my pH plus my POH is equal to 14. So if I know my pH is 2.051, 14 minus 2.051 is equal to 11.949, or roughly 11.95. What concentration of HCl is needed to neutralize 80 milliliters of a 0.8 molar solution of NaOH? All right, monoprotic, monoprotic. So if we were going to do the normality equation, N times M times volume has to equal the product of N2, M2, V2. So what concentration? The N's are both equal to 1, so I don't really need to consider normality constants here. For the concentration, so this will be our unknown, is needed to neutralize 80 milliliters of a 0.8 molar solution. Sure, it would be nice if I actually got a volume. What concentration of HCl is needed for this? Well, let's just assume, and I'll just make this up as we go, that we have 25 milliliters. 25 milliliters of HCl to neutralize 80 milliliters of 0.8 moles per liter NaOH. I'm going to need a concentration of HCl. Let's just do HCl is equal to 2.56 moles per liter.